Thank you, Melissa, and thank you for the organizer for inviting me. So it's a real privilege and a great pleasure to be here at this wonderful occasion, to be able to talk, to celebrate Jim's birthday. So bon anniversaire, Jim. And okay, so maybe first I would like to explain a little bit my title. So certain refer to a well-known paper by Fredon on certain L functions. So by which I would like to say that my goal is to try to add certain items to Borel desiderata on what Langlands correspondence should, property that Langlands correspondence should satisfy. And so there are essentially three desiderata. So, and it is explained my word expected. By expected, I mean what Gio was saying yesterday as a conjecture theorem, meaning in general it's conjectural, but in many cases it is proved. First one is cuspidality match, which means cuspidalities, which means that on the side of representation of PAD group, we have a notion of cuspidality, which is well known, which come back to Harischandra, which is the notion of supercuspidal representations. So what I would like to have is an analogous notion on the Langlands side. So for GLN, it's just irreducible representation of the absolute value, but more generally what it is. And this is what I will try to explain. Now, second thing is Bernstein decomposition. So we have Bernstein decomposition again on the group side, and we want to have something similar on the Galois side. And now, third thing, so these are, are new, but for it's in comparison to Borel work is of course new, but Corvallis, but we have this already for a few years ago. Now, as you have seen here in both Monday and yesterday. So on Monday, we have several talks on unitary dual, which involves not just a single irreducible representation, but the Grothendieck group of representation. So a linear combination with possible negative coefficient of irreducible representation. And yesterday also, for instance, in Tasho's talk, we have identity of characters, which also involves signs. So I would like to have a notion of kind of generalization of cuspidality in this setting. And another thing to say is that, of course, supercuspidal are the building blocks for the representation theory of PAD groups. But for some reason, in many cases, we are especially interested in temper representations. And for temper representations, and actually for the Langlands correspondence, thanks to the work of of Silberger and Sink, it's enough to have to understand, construct the Langlands correspondence for the temper representation. So I have a question for you. What are, in your opinion, the building blocks for the temper dual? For not the temper dual, for the temper representations. Okay, good answer. Discrete series, of course, unitary supercuspidal should be there. Yeah. More generally, discrete series. That is not enough. So maybe people for real groups can add something to discrete series. Limit of discrete series, which for PAD are elliptic representation. But it's better to quote, to have a good author to say that. And so let me write something. Suppose that G of F is a real or PAD group. That is, G is a connected reductive algebraic group over a local field F, which we take to be of characteristic 0. harmonic analysis on GF is built upon the set of irreducible tempered representation of G of F. These representations include the discrete series and consist in general of irreducible constituent of representation induced from discrete series. We shall be interested in the subset of elliptic representation in the tempered dual. The elliptic tempered representation also include the discrete series and can be regarded as basic building block in the tempered dual. And the purpose of this paper is to study some property of their characters. And who is the author of this wonderful note? Of course, just Arthur. And it is taken from his amazing paper on elliptic tempered virtual characters, which was published in Acra Math in 1993. And this is great because it says to us that you should consider elliptic. So maybe I should say what is an elliptic representation. It's a representation, an ordinary representation. I mean, irreducible representation is elliptic if its Harry-Chandler character does not vanish on the set of elliptic regular semi-simple elements. And elliptic means that the maximal split component of the center of the centralizer of the element coincide with the maximal split component of the center of a group. So these are the elliptic. But here we have, I told you that you need more of just irreducible representation, but virtual ones. And here is an example, which is not on periodic, but it would show you what I have in mind. Take just GL2 over a finite field and consider the trivial representation and the Steinberg representation of GL2. Of course, they are not cuspidal, so their Jacquet modules are not, so there is only one levy to consider here, so which is the split torus of GL2. And if you compute the Jacquet restriction, this is G. And if you compute the Jacquet restriction for the torus and the split torus of a standard Borel of 1, and then this is equal to the Jacquet restriction of a Steinberg. So I can write this like this. If I consider the difference of 2, it's 0. So 1 minus Steinberg has to be considered as cuspidal. And actually, it can be viewed as a cuspidal function, not a cuspidal ordinary representation, but a cuspidal function. So here, what I would like to consider is elliptic virtual representations. I consider that, yeah, for finite group, everything is tempered, in my opinion, but we can debate on that. But okay, and why I give you this is because we have something similar here in the setting of Jim. So in that paper, Jim also introduced the notion of super tempered character, which is a character that are tempered, but they are more than tempered, and show that the virtual elliptic character that he constructed in the paper are super tempered. And a few years later, Rebecca Herb studied this and proved that this character are actually all the super tempered virtual character. And and also there is an equivalent characterization for a virtual character to be super tempered is that its weak parabolic restriction is 0. So you replace the Jacquet restriction, Jacquet modules or parabolic restriction by the weak Jacquet restriction, or if you prefer the weak constant term. and then you get 0. So this has to be this virtual character, in my opinion, should be considered as cuspidal object in this new setting. And my hope is to study what we have on the Galois side attached to them. So this is not yet fully done, but you will have some result in that direction in the talk. Okay, so briefly, some notation. So F is a non-Archimedean local field. The WF is its absolute Weyl group. At some point, I will also need the inertia group, IF, and G will be the group of F point of a connected reductive algebra group G. And I will denote by G check its Langlands dual. So now come to the L parameter. Okay, for my purpose today, it's this version of Langlands parameter is easier to use. So I will take this instead of the one with a GA. And I will need an enhanced parameter. So why I will need to already for the first item, because as you know, for instance, if you arrive already in SP4 or G2, as the smallest examples, we find L packet, which in general may contain at the same time some representation which are supercuspidal and some that are not. So there is no hope to define a notion of cuspidality for the parameter itself. So yes, you need the enhancement. And the enhancement is an irreducible character of a certain group that I will denote for now A5, which is attached to phi, and I will come back to this later. So what we did with Ahmed Moussaoui is here, and Martin Soloved, we solved the item 1 and 2. And more precisely, what we did is that we show that the set of G-check conjugacy classes of enhanced L parameter first admits a natural decomposition in Bernstein style according to certain inertial classes of their cuspidal support. So it means that we have a notion of cuspidality that I will explain. And moreover, each such Bernstein block on the Galois side occurs to be in bijection with the simple modules of a certain Hecke algebra attached to the S, which means that we have something more. So here it's just a set, but the Hecke algebra, so the simple modules correspond to that set, but the Hecke algebra arrive with all its representations. So we get some Avar representation of that Hecke algebra, which should correspond to something, which I don't know what it is, on the Galois side. So the simple modules are enhanced L parameter, but the rest of the algebra is not yet understood what should be the interpretation. Yes? Sorry? Galois side. Only Galois side. Yes, on the group side, we know what we should have. Yeah. But on the Galois side, it's more mysterious. More mysterious, but at the same time, in general, it's easier. Okay, so briefly, Alexandra resolved that you all know probably, so that any irreducible representation occurs as a component of some parabolically induced representation from some supercuspidal irreducible representation of a Levy subgroup. And the G conjugacy class of that pair formed by the representation, well, the Levy and the supercuspidal is uniquely determined, and we call it the supercuspidal support of a representation. So this was Alexandra, and then Bernstein arrived, and so we have Alexandra series, and one of the ideas of Bernstein was to group together all the Alexandra series which have a property that their supercuspidal support are close enough. And by close enough, I mean that the representation sigma and say sigma prime belongs to the same orbit under the action of a group of unramified character of L. And so I can phrase it in more detail like this. So I will denote by L1 the subgroup of L generated by all the compact subgroup of L. If you have questions, you can ask. And the group of an unramified character, I will denote it by X and R of L. By definition, they are the characters which are trivial on L1. And I will denote by frac S the G conjugacy class of this pair. So in Aishana, the supercuspidal support was the G conjugacy class of L sigma, and here it's the G conjugacy class of L and the orbit of sigma by the action of the group of unramified character of L. And to have a different notation, I will write it as L. So this is when I put just this parenthesis is conjugacy class, and here is inertial conjugacy class. And sometimes I will need to consider especially the case where L is equal to G, and I will denote it by SL. And then I will denote by B of G the set of such classes S, and it is a countable infinite set. And with this, you can state Bernstein decomposition of a category of smooth representation of our group G as a product of a full subcategory Rs of G, and the category is defined to be the subcategory, the full subcategory of R of G, whose objects are the representation, such that every subquotient of pi has its supercuspidal support contained in the inertial class S. But Benjamin told more to us. The following. So if capital pi S is a progenerator of this subcategory Rs of G, then the functor which sends V to the homomorphism from G homomorphism from pi S to V gives an equivalence of category between this subcategory and the category of modules of the endomorphism algebra of that progenerator. I mean, this is an well-known result. I mean, it's not due to Bernstein, actually. This is well-known, but what is due to Bernstein is the definition of a progenerator. But I will. So there are different possible choices for the progenerator, which will give you different algebras, which are not necessarily isomorphic, but which will be Morita equivalent. And some choices are better than, I mean, each choice has its own advantage. So if you take the smallest possible generator, you will get the most precise algebra, which is the best. But this one is also more difficult to study. I mean, so here is I will give you an example with this smallest one. So I would just consider sigma 1 an irreducible component of a restriction of sigma to L1, and then induce compactly from sigma 1 from L1 to L. And you can check that this induce that I denote by pi LS does not depend on the choice of sigma 1. And then when you have this one, you induce it from L, parabolically induce from L to G. And you get a progenerator of the subcategory. Okay. So you would like to do something in this spirit on the Galois side. So first thing, we need first the analogous group of, the analogous object of the group of unramified character. And this was given to us by David in his paper on local Langlands correspondence. It was also studied later on by Haynes. And this is this group. So I take the center of G check, the invariant by the inertia group, and then connected component and the co-invariant by the action of a Frobenius. Okay. Yes.
If G is semi-simple, the center is trivial. That means nothing there.
Yeah. Yes.
That's interesting Bernstein component.
You have interest in Bernstein component, but even yes. Yeah, it's for the levy. Yeah, yeah.
Okay. So
I will apply it to the levy. So you. So this is just a definition. I'm sorry. So this is the definition for an arbitrary PID group, and as Jessica said, I will apply it to the levy. And in fact, this group is canonically canonically isomorphic with what it is with X and R of G. Okay. Okay, I think this is kind of easy, and but what is more subtle is to define what should be cuspidality on the Galois side. And for that, I will leave this word of PID group for a while and consider just complex reductive group. So forget everything and start again. So curly G is a connected reductive group defined over C, and P is a parabolic subgroup of G with some Levy subgroup, curly L. And I will consider the following algebraic variety. So the element in curly G, such that, so I fix two unipotent elements, U in G and V in L. And I consider this variety of a set of elements in Y in G, such that the conjugate of U by Y belongs to the coset VU with an action of G. So G and the parabolic act naturally on this on this. And so at first sight, perhaps this variety looks strange to you. But if you think a special case where the levy is just the torus, so if the levy is a torus, what could be V? A unipotent element in the torus. The only possibility is V is the trivial element. So V disappears from the picture, and you just take the element in G, just that the conjugate of U is in U. And if you think of it a little bit, it's just the Springer fiber of U, the set of Borel subgroup that contain U. So the idea of Lustig was to generalize the Springer fiber by using this new variety. And they are nice for the following reason. They have action on them by two groups. The group of components of a centralizer in G of U, that I like to denote it as AG of U, and also the AL of V. So the group of components of a centralizer of V in L. So it acts on that variety, and more precisely, it acts on the set of irreducible component of maximal dimension. So here is the value of a maximal dimension. So using this, you see that you have a permutation representation, which corresponds to this action on the set of irreducible component of maximal dimension. Okay, you have a group, you have a representation, and what you would like to do? Parabolic induction, Arishona philosophy, parabolic induction, cuspidality, and so on. Okay, that's what you do. So take rho, an irreducible representation of that group, and call it cuspidal if for every unipotent V element V in L, rho does not occur in this permutation representation. If it's for any proper parabolic subgroup, which I phrase it like this, if it's occurs, it implies that the parabolic has to be G itself. Okay, so we have a notion of cuspidality for that group. So now Lustig was considering a group which is curly G, which is connected with Ahmed and Martin. We extended it to the case of disconnected group. Okay, there are a lot of things that we can say in this setting, but I wanted to keep things as short as possible. And an easy way to say that is first to observe that if I denote by G naught the identity component of G, the group of component A G naught of U is naturally embedded in A G of U. And we can define a notion of cuspidality by saying that rho, or the pair U rho, is cuspidal when rho is now if it's an irreducible representation of this group, AG of U, and we call it cuspidal if the restriction of rho to the smaller group is a direct sum of irreducible representation rho naught, such as one, and it's equivalent to say any of them, is cuspidal. So here I phrase it with pair cuspidal, but U is fixed, so you can, the cuspidality is in fact on rho. Okay, so we have a notion of cuspidality, which is due to Lustig for a connected group, and that you easily extend it to disconnected group. Okay, but Lustig do more. First a remark, which is already in a Lustig paper. So it's an old paper from 1984, the paper where he defined generalized Springer correspondence. And he made this remark: if I take C, the G conjugacy class of U, then of course, if U rho is cuspidal, the class is distinguished, meaning that that unipotent class does not meet the unipotent variety of any proper Levy subgroup of G. However, in general, not every distinguished unipotent class supports a cuspidal representation. And this is exactly what happens, the situation that you will see if you look at L packet for the example that I was given to you before. So if you look at an L packet for SP4, which contains so if a packet contains cuspidal representation, then you will have some pair which is cuspidal, but we have some distinguished L packet which does not. Some L packets such that the corresponding unipotent element is some L packet that unipotent element attached to phi. So the image by phi of the standard unipotent element of SL2 is distinguished, but the packet does not contain any cuspidal pair. Okay, maybe I'm going too fast on this, so it was just a remark. So now my goal now is to use this result to what I was already saying vaguely, to use this in order to understand better the Langlands correspondence, and more precisely to define a notion of cuspidality on enhanced L parameter. So for that, I need to know what are enhanced L parameters. So parameter, I told you what it is, but I need to tell you to define the rho. And for that, I will use another paper by Jim from 2006. A very short paper, not on L packet, but we contain several very interesting results and especially a conjecture and very important conjecture. So Jim attached to an arbitrary L parameter for an arbitrary PID group G the following group. First, the group which here I will denote by S phi SC. So first I will consider what showed up already in several talks yesterday, the centralizer and on Monday also, the centralizer in G check of the image by phi of W prime F, where W prime is the Weidelin group, what you want, but in my case it would be WF plus SL2C. And when I have my group G, the dual group, G check, I will consider its adjoint group, and I will denote by G check SC the simply connected cover of a derived group of G check, which is also the simply connected cover of a derived group of G ad check. And then I will consider the pre-image in that group G SC check of the image of S phi in G ad check. So this is the group that you will find in Jim's paper if you look at it. And you also find we will also find this exact sequence. So we have that group in the middle. I mean, the group of component of that group. Here, the group of component of S phi, and that group of component is an extension of this one by the group of component of the center of a GSC check. Okay. So when I gave a talk a few years ago in Singapore on our work with Ahmed and Martin, using this, and my enhancement would be an irreducible character of a group of component of S phi SC. And then after my talk, someone came and told me that I was wrong, that I didn't take the correct group and that our results were clearly false. Okay. So I didn't worry much, because if I was wrong, it was not me who was wrong, it was Jim. And I cannot believe this. So I was very confident. But still, I would like to know why people have doubts. And then I found a very nice paper, and very interesting paper by Tacho, in the case of group of characteristic 0, and which was later extended by Peter Dearly for group of positive characteristics. So forget for a minute this. No, not forget, because I would need that. Sorry. So I need to explain a little bit more. So I will call G star the quasi-split inner form of G. And I will denote by IT of G the equivalence classes of inner form of inner twist of G, which are the same as, of course, the inner twist of G star. And when I take an element, so inner twist is much better than just inner form, because you may have two inner form which the same inner form which may give you different inner twist. So it's much better to rigidify a little bit the situation by adding this psi. So not view just so G prime is the inner form, but you need something more, the isomorphism attached to it. And then we have this. So all of this is in the paper from Jim from 2026. You can consider a character of the center of GSC check, which is element of a center which are fixed by the absolute Gala group of F. And then you have a bijection, canonical bijection between the inner twist of G with H1F of G star add, and a bijection here which is due to Kotvitz from this to the set of irreducible character of that group. So I can consider the subset. So I told you that I would consider a representation of a group of components of SC. And sorry. And I would denote this by ir zeta xi of pi 0 phi SC, the subset of ir pi 0 phi S phi SC of a rho, which have the property that the restriction of a central character of rho to that group is an extension of that character, of a character which zeta xi. And I will denote by phi E. So phi is for parameter, E is for enhancement. So the set of enhanced L parameter, which are the right to consider for G prime xi. So I will call them G prime xi relevant. So it's possible to make a precise definition, and we can. It is already in Borel Corvallis paper, the notion of relevance. So, and these are this set phi E G prime xi is the set of enhanced parameter that should correspond to the irreducible representation of G prime by the local Langlands correspondence. So now the explanation of why I was not wrong, but is the following. So due to character when characteristic f is 0 to delay when characteristic f is positive, is the following. So you introduce another group, which is this one. So the quotient, so you do it for the quasi-split form of G. So you consider the quotient of G star by what I denote by Z there, which is the center of the derived group of G star. And then we use this complicated notation to denote the preimage of the fixed point of the center of G star check by gamma f under the natural isogeny from a G star bar check to G star check. So we have this group, which is a quotient of this. So you go to the dual side and you get a natural surjective map that way. And you view now a G as a rigid inner twist of G star, which I will not explain, but it's very important. And it means that you will rigidify more the inner twist of G star. And in particular, a rigid inner twist comes with a character that I denote by zeta G plus of this complicated notation group. And I will denote by S phi plus the preimage of S phi. So S phi does not change, it's the centralizer in G check of the image of phi. And under the preimage under the same, again, under that map. And then you will find in Tachot paper that there is a canonical proof that there is a canonical isomorphism between the group defined by Jim and this group, which is more complicated. But so this isomorphism is not canonical, but it induces a canonical bijection between the set of irreducible of the set of character of the component group of each of them when you put here the corresponding character. And that bijection is very easy to define. You just start with an character rho here, so an irreducible representation of that group of components, and you tensor it by the character which is defined by Jim in his paper. So I think the person who asked me a question was thinking that I should use that, and it's perfectly right, but I am also allowed to use the other version. And I would say that for some situation, probably one is better, is more adapted than the other. I'm not sure, but I have a feeling that it's a bit like the two way of considering L parameter. You have two way, and both are good, but in some circumstances, one is more adapted to what you would like to do than the other. Okay, but anyway, my project was to explain to you how to use generalized Springer correspondence, and to do that, you can do both of them. But the most important point is, which was noticed by Ahmed in his thesis when he studied the case of split classical groups, is that if I denote by U or U phi the image by phi of the unipotent element of SL2C, and I consider the group of components of the centralizer of U in U phi that I denote by A G phi of U, but then the group of components of Jim's group is canonically isomorphic with that group A G phi of U. And if you prefer that setting, you have exactly the same thing. So you here the group G, you define a group G phi plus, which is the preimage. Instead of taking the preimage in GSC check, you take the preimage and in G star at check. And then you do the same, and again, we have the same kind of isomorphism. Anyway, in both situations, which are actually the same situation, very closely related, you have the possibility to view the irreducible irreducible character of that group of component or that group of component as the irreducible representation of this group. But I like this group, or I also like this one, for the reason that I can take for G phi or for G phi plus the curl any, I mean, it's a reductive complex group, in general disconnected, but anyway, and you can apply to it generalized Springer correspondence, and in particular, you can apply to it, you have in that group a notion of a cuspidal unipotent pair. So this gives me the definition. So an enhanced L parameter is cuspidal if it is the parameter is discrete. We know, or we knew already that we needed that condition, but also that the pair U phi rho is a cuspidal pair in the sense that I have defined. And then we conjecture that there should be that Langlands correspondence should provide a bijection between the set of equivalence classes of irreducible supercuspidal and Jussieu conjugacy classes of cuspidal enhanced L parameter. So this is this first desideratum. And it is proved in many cases, for instance, for GLN, SLN, every pure inner form of a quasi-split, I forgot something, every pure inner form of a quasi-split classical p-adic group. Not all of them, it would be too great. And also when P is not equal to 2 or 3 for G2. Okay, so then I have everything. I have Bernstein analogous statement. So I can consider the orbit of I can consider this cuspidal object attached to a levy and the action of a group of anamorphic character of a levy on the dual side on it. And okay, and I have this notion of S check. Then, and I will probably skip this because time is flying. So just very briefly, if I told you that I would like also to define an equialgebra on the Galois side. And in that case, the group to consider is, as you can imagine, the pre-image of a centralizer in G-check of this time, not of all the WF, but just the inertial group. And if you do that, you can attach to that group a root system and also a root datum and also parameter function, weighted function. And with all of these data, which were built on what Lustig did for in a particular case, you will arrive to the construction of an equialgebra. Okay, I will skip this because it's very technical. If you can read the notes, if you are interested in it. And but the nice point is that algebra is a twisted affine equialgebra, meaning that you have an honest affine equialgebra with possibly an equal parameter and semi-direct product with a the twisted group algebra of a certain finite group. And of course, when you find this, you wanted to know if we have examples when it is actually twisted, that there is a non-trivial cocycle. And to do that, we went again reading the paper by Jim on not on L packet, in which he gave a very interesting example in SL2, where the group S phi SC is not commutative. And using that group, it's possible to build an example in SL8 for which, for SL2, the algebra, I mean, the example in Jim's paper is for supercuspidal representation. So there's no hope to build something for an algebra, but we use it in the levy, and considering a levy which has one part is which is a certain levy GL2 sorry, in SL8, four copies of GL2 intersected with SL8 over F. you of SL8 over G for division algebra, you can cook an example in which a co-cycle is not trivial. Not. So, okay, so what we expect is the following. So on the group side, we have an generalized Hecke algebra, which was given to us by Bernstein. And for classical group, it was studied by Heyermann, and we know exactly that it is an honest extended affine Hecke algebra. And for other group, Soloway studied it also in many cases and found that it is a twisted Hecke algebra. And so what we expect is the following. Our conjecture is that Langlands correspondence will give us, will match the representation, the modules of that algebra which have finite length with the module of this algebra which have finite length. So we do not expect in general that the two Hecke algebra are isomorphic or even Morita equivalent, because it's not the case for inner form of SLA. But this is true, this statement is true for inner form of SLA. And we also expect, I mean, it is related to that if, when I say S corresponds to S check, I mean by using my first desideratum, then the corresponding finite group, the normalizer of S mod L and the normalizer of S check mod L check, which are extended finite Weyl group. By extended finite Weyl group, I mean it's a semi-direct product of a finite Weyl group. By this group RS or RS check, we expect that these groups are isomorphic. And again, when we have Langlands correspondence explicitly given to us, we can check that it is indeed the case. Yeah, of course.
On the last slide, how do you see the two algebras are not Morita equivalent?
Because we computed explicitly what they are, and you see that it's not it cannot be. Okay, I can explain to you later in more detail. Yeah, but it's a very good question. Yeah. Okay, so. Okay, I would like to go quickly to this result. So we apply with Ahmed and Martin this. So I use this strategy also with for inner twist of GLN, SLN, and also for G2 with UG2. But the most interesting case that for today is the fact, not just today, but in general, is the case that we can apply it for classical group, for pure inner form of quasi-split p-adic classical group, meaning symplectic special orthogonal or general spin group and unitary group. So this is, I mean, similar result as for G2, but for this group, we have more. We have this book by Jim and the addition that Tashu explained yesterday. And we check that the bijection that we obtain by comparison of the Hecke algebra on both sides of the correspondence coincide with the correspondence which is obtained in the book.
Sorry. So
yes?
One of the classes of groups you say this applies spin groups.
G spin, yeah, spin and G spin, yeah.
Which not spin.
No, not spin, general spin. Yeah. Yes. And the reason is because for that, we benefited from work of Colette Meuglin, which extended some result of James Arthur to this kind of group. And but in particular, we didn't do spin, and we also didn't do GSP.
But a lot of the slides you showed us had to do with non-pure.
For non-pure, it would be very interesting, but
you spent a lot of time showing us things about non-pure inner forms and how you make Langlands parameters,
but this result is only for pure inner form. Yeah, I'm sorry. Hopefully in the future we'll have more to say, but for now it's just that. And but my time to say any group was because of this. And I wanted to tell you something about the elliptic setting. So on the group side, we have a natural way to think of, to define a scalar product for temporal representation, which is given by the Euler-Poincaré product. And of course, the Euler-Poincaré product is not, as a radical, as a non-trivial radical. So, and this comes back to work of Kashdan. So we can consider, we denote by R of G prime. So G prime now is any inner twist of an arbitrary inner twist of G. And I consider the quotient of the, so I denote by R of G prime the span, C span of the irreducible representation of G prime, and by R bar of G prime, it's the quotient of R of G by the radical of the Euler-Poincaré product. And I would like to give you an elliptic product on the Galois side. And this is very much inspired by the paper I was mentioning at the beginning of my talk on elliptic temporal character by James Arthur. And it's defined like this. So this is for a finite group. Any finite group will, and you fix some, consider some finite dimensional representation delta v delta of that group. And you take just the sum for all the elements of the group, evaluate the determinant at 1 minus delta, and then the product of F1 A minus 1 and F2 of A. And you can define also a certain quotient. So you look at the radical of that form, and you can check that it is the subspace of element in R of A, which are spanned by induced representation of proper parabolic subgroup of A. And you take the quotient, that is what I call R bar. And two things I would like to say. First, this allows us to have a notion of elliptic element. So we say that an element in A is elliptic if the vector space V delta has no fixed vector by delta of A, non-zero fixed vector. And if I denote by L of A the space of class function of A which are supported on delta elliptic element, then you can easily check that if it is in bijection with R bar of A. Yes?
There is no capitalness assumption.
No, because this A is a finite group.
No, but just before, the slide before.
The slide before for the Euler-Poincaré product, yeah, is for tempered.
Sorry?
Yeah, this is, okay.
Of course, this is defined generally. But
No, okay, yeah, you are right, but so this is defined generally, but you take the quotient. But in fact, now, if you consider now just the tempered one and you take the quotient, you will arrive to the set. So
this is what you want, the bottom.
Yes, this is what I want. But now, if I, instead of taking arbitrary representation, I only take the space, which is the C spans of Ir temp of G prime, and I take the quotient, I will get the same quotient. There is isomorphic.
It's the same?
Yeah. So you just view, in fact, the tempered. And of course, I will like to apply these things where A is a group of components of a centralizer of some element. And I will need a unipotent element or semi-simple element, depending what I would like to do. So I will skip this because probably not enough time, but just one thing. So my notion of ellipticness or ellipticity, I don't know what I should say, depends on the choice of a representation delta. And so in my group A is an arbitrarily finite group, I do not have a canonical choice. But if my group is the group of components of a certain element, the centralizer of a certain element G, then there is a natural way to define a representation delta, which is explained here. And then it is that kind of that representation that I will use in my application to local Langlands. And so if phi is an L parameter, I will call delta phi this delta when G is U phi, so the unipotent element attached imaged by phi. This would be when, in the case of pure inner form, so this is the P, and delta phi plus for the other case, I mean, say the rigid inner twist case. Okay. So I am not sure if it is understandable. So I defined to you before a group G phi plus for in the rigid inner twist setting. And here I am defining another group, which is in the setting of pure inner twist. Okay, maybe I should have said that. When you look at the pure inner, the rigid inner twist setting, in the definition of your inner twist, your rigid inner twist, there is a certain germ. And if you take for that germ a trivial germ, you are in the setting of pure inner form. So you recover the pure inner form as a special case of a general situation. But this is not me. I mean, it's in Kadeta's work. Okay, so but you have this. I define this delta phi or delta phi plus, depending on what I want to have. Sorry, delta depend on phi. Yeah, delta depend on G. But for me, G will be U phi. Will be the unipotent element imaged by phi of a standard unipotent element of SL2. So so it's why I delete it from a notation, because it is given by phi. But it's a good question. Okay, so I will skip this. Unipotent representation of special case. And okay, actually, okay, I will skip. Oh, no, maybe not totally. Okay, I will consider L parameter, which are trivial restriction to the inertia group. So I do not know a good name for this parameter. So strictly speaking, I should call them unramified, but on the group side, it does not correspond to unramified representation. We can call M unipotent, but it's also misleading. So maybe a possible word should be residually unipotent, because they correspond in general to representation of a p-adic group, which are obtained from a representation of a finite group, the reductive quotient of a certain paraoric subgroup, which are unipotent in the sense of Lustig for finite groups. So maybe residual unipotent or FQ of KF unipotent. Anyway, but for this representation, which are particular representation, then with Chibotalo and with Dan Chibotalo and Bev Romano, we prove the following, that the Langlands correspondence gives an isometric isomorphism between these two sets. So here we consider pure inner twist, and what I call R U bar is the image in R bar of G prime of a space spanned by the residually unipotent irreducible representation of G prime. And when you apply local Langlands correspondence here, you get here you get also R bar for this group of components. So we prove this when the group G star is split and adjoint, and also when G star is SLNF, or G star is SP4 for all the pure inner twist of G star. And I will finish on this. It's a conjecture. Okay, so when I have to admit that I mean, this conjecture is very new. And when I stated, I was wondering what should be the correct setting, if I should use rigid inner twist or not. My believing is when you have one fixed group, it does not matter. But when you have several groups, it's probably better to rigidify as much as possible. to make the things more better. So I will take the direct sum of all the rigid inner twists of G star and consider R bar of G prime. And then I expect that local Langlands correspondence here will give us an isometric isomorphism with respect to the Euler Poincaré product here and here the elliptic product with delta phi plus. And this conjecture, it was possible to, so the proof is I mean, I have to finish the writing, but I have no doubt it works. In the following setting, when the two ecoalgebra are almost Morita equivalent, because I need to pass at some point from the group side to the Galois side, and for that I will use our ecoalgebra. And at least there, I only need that there to have a bijection between their simple modules, actually. And of course, I need that the S, the cuspidal object, which give me the ecoalgebra correspond by local Langlands correspondence. And also, at the moment, I hope it will make progress later, I need that the group DWS and WS check are actually finite by group, Coxeter group. Because if I mean, it would be more work if I consider the semi-direct product with this this kind of R group. And so, I mean, this is, I don't know, but in this case, it's possible to establish the conjecture. Okay. And I will thank you for your attention.